Nice to meet you. I'm Khatar Chuktai, and you're watching my YouTube channel, School of Mass Chemistry. I'm going to discuss live marathon session for organic A2 chemistry students, especially for the Cambridge students. Without further delay, let's get started. Basically, I'm going to start from the organic chemistry basics, that is benzene ring. What is a benzene? What are its basic properties? Number one, in this case, the benzene ring, this one, this is the typical diagram of the benzene ring. I mean, in this structure, in this benzene ring, there are 3 triple bond and 3 single bond. So these are called pi bonds. These bonds are said to be pi bonds. And these 3 are called sigma bonds. So it means that this benzene ring, that is over here, it's having 3 pi bonds and 3 sigma bonds. It's also having 6 hydrogen atoms attached to its carbons, and each carbon is attached with the 1 hydrogen atom. But in fact, indeed, these 3 pi bonds are not localized. They are not fixed as they are indicated in this structure. So this is the not actual structure of the benzene ring. Here is the actual structure of the benzene ring. This is called skeletal formula of the benzene ring. Each corner is having hydrogen atom. Once again, 1 carbon, 1 hydrogen, but here is the delocalization of pi electrons. So actually, as far as my opinion is concerned, you will have to write this one. You will have to report this one, benzene ring, this one structure, that is the most appropriate or one of the appropriate structure for the benzene. As far as the nomenclature, benzene name is concerned, benzene is a naturally occurring compound. But this one, that is having alternative double bonds, 3 double bond and a single bond, double, single, double, single, double, single. This is in fact, it's not a benzene. Here there is the demonstration of fixed 3 pi bond. But for the sake of simplicity, yes, we can report this structure as well. This structure is also valid in your syllabus. You can write, you can report your answer with the help of this structure. But actually, this is the format, this is the basic structure of the benzene ring, in which we put this circle, mean pi electrons are exclusively, they are 24/7 delocalizing on the benzene ring. This is hexagonal planar structure. Its structure is basically hexagonal planar structure. Each carbon atom is having 1 p orbital on it. So the basic backbone of this benzene ring is made up of carbon, basic sigma bond. These all are carbon sigma bond, and each carbon atom is hosting 1 p orbital with the 1 electron, so they can make mutually pi bond between them. As you know, pi bond is formed between 2 parallel p orbital, so 2 adjacent parallel p orbital can overlap and they can form 3 pi bond or double bond. So basically, it's a hexagonal planar structure. It is having the ring that is composed up of 6 carbon atom, and each carbon atom is basically having pure p1 orbital, 1 pure p orbital on each carbon atom. Because of this p orbital, they can make overall these 3 pi bonds. But as I told you, these pi bonds, these double bonds are not fixed. They are not localized. They are continuously moving. They are showing break and make with the other p orbitals. Same is the case over here. So they are continuously moving. Electronic clouds are moving pi electron clouds are moving above and below the plane of the benzene ring. Next thing is carbon-carbon bond length is pretty same, and the bond angle is equal to 120 degree. I mean, this one bond angle that is reported as CCH bond angle is equal to 120 degree. Same is the case, this one bond angle, I mean CCC bond angle, that is also equal to 120 degree. So all bond angles, again this one is HCC or CCH, this one bond angle. So all bond angles around the carbon atom are 120. So generally speaking, as I told you, it's a hexagonal planar structure. Wherever the bond angle is equal to 120 degree, then the structure is said to be planar structure. Any shape, any molecule that is having geometry with a bond angle of 120, that portion will be said to be a planar portion, a planar structure. So this molecule is a flat molecule. All carbons, all hydrogens, they all are lying in a single plane. Next thing, all carbon atoms in the benzene ring are sp2 hybrid carbons. I mean, if you want to know the hybridization, here is my rule, simple rule you can say, just check the total pair of electrons around that carbon. So generally speaking, find the total pair of electron around that atom. Here is a carbon atom. So 1, 2, and 3. You will count double bond as a one pair. You will count triple bond as a one pair. So totally there are basically 3 total pairs surrounding this carbon atom. So I mean answer is equal to 3. The 3 answer mean its hybridization is equal to sp2. What does it mean? What does it mean? sp2 simply mean in the simplest version of sp2, you can say this carbon is having 3 sp2 orbitals around it, and it is making sigma bond by these orbitals. Each carbon is making sigma bond, 3 sigma bond around it, and in each sigma bond it is using sp2 hybrid orbital. I mean, carbon has mixed one s and 2p its outer shells orbitals to degenerate, to reform, to make new pair sp2 hybrid orbital. These all three sp hybrid orbital are having same energy and same shape. So once again, all carbon atoms are showing sp3 hybridization, and all carbon atoms, even this is a double bond, this is single bond, but you know the double bond is a shorter bond in normal routine, in a normal alkene, but in this case double bond is, and the single bond is having same length. Double bond and single bond both are having same length in the scenario of benzene ring. Why they are having same length? As I told you, double bond is a shorter as compared to single bond. Same is the scenario with the triple bond. Carbon-carbon triple bond is the shortest one. Then double bond is the shorter, and carbon-carbon single bond is the longer one. But here is the delocalization of pi electron. So each carbon-carbon bond is not a simply single bond. Each carbon-carbon sigma bond, or each carbon-carbon bond, generally speaking, in addition to the pi bond as well, pi plus sigma bond I'm going to talk about basically, overall character of each bond is almost equal to 1.5 character. I mean, no one bond is purely sigma bond or one bond, and no one bond is purely double bond and having, I mean, one sigma and pi bond. The effect of pi electron is equally distributed on the benzene ring. So that is why all carbon-carbon atoms are having same bond energy and same bond length. The next thing is CH bonds are sp to s overlap. So one carbon atom, as I told you, one carbon atom is offering 3 orbitals around it. It is having 3 hybrid orbital. The name of these all 3 hybrid orbitals is sp2. And whenever hydrogen is coming to make covalent bond with a carbon, it is having only one s orbital. So hydrogen cannot have any sort of hybridization. So hydrogen is offering s orbital, carbon is offering sp2 orbital. So carbon hydrogen bond is composed up of ssp2 or sp2 s overlap. This is called overlap. I mean, when the two orbitals overlap to each other, there is the formation of a covalent bond. And here is ssp2 overlap. Same is the case when two carbons are supposed to make a bond, sigma bond. Once again, I'm going to talk about sigma bond. When two carbon atoms are going to make sigma bond mutually between them, then they are going to overlap through their hybrid orbital. Both carbons are showing sp2 hybrid orbital. They are overlapping their orbital. They are going to then share their electrons and so on. So that is the basic story or history of the sigma bond present in the benzene ring. Now, as I told you, carbon-carbon double bonds, all carbon-carbon double bonds, those are 3 in numbers basically, and they are going to be formed by p orbitals overlapping, and those are parallel p orbital. Once again, each benzene ring is an aromatic compound. It is having extensive delocalization of pi electron, and generally speaking, that is the same behavior of the arenes. What are arenes? Arenes are the compound having benzene ring. Any compound, any organic compound that is having benzene ring can be known as called as arene, as far as your syllabus is concerned. So arenes as well as the benzene both are having a special character that is called aromatic character. Now come toward the next one. The next one is nomenclature. How to give the name of different organic compounds, especially as I told you, aromatic organic compound are arenes. So this is one row that you can use to give the organic compounds, name the organic compounds. Here is two special name in the organic compound, and here you are having different two type of major functional group. I mean, one is the major and other one is the minor. Here, in case of halo group, in case of alkyl group, in case of nitro group, the name is quite simple. Its name will be chloro if there is Cl, chloro if there is Br, bromo if there is iodo. So chlorobenzene, the complete name benzene is written over here. Same is the case if alkyl group is present, we will write the name of alkyl, this one, substituent methyl benzene. And here is the, again, as I told you, if the nitro group is present, the same format will be used. Here is a nitrobenzene. So chlorobenzene, methylbenzene, nitrobenzene is a style of writing the compound. Those are having these group, halo group, alkyl group, and nitro group. But if the benzene is having OH group, is a special group, or if it is attached with NH2 group, amino group, again its name will be the special name. Its special name with benzene ring plus OH group is equal to phenol. So you will write its name as a phenol. What is the name of this compound? This compound is basically, sometimes it is known as aniline. It's a common name once again, or phenylamine. Phenylamine. Basically, what is the phenyl group? This one group is called phenyl group. I mean, benzene ring that is having overall 6 hydrogen and 6 carbon atoms, C6H6 is benzene. But if I am going to replace one hydrogen by any other atom, by any other element, you can say, other than hydrogen, then it will known as phenyl group. This groups, that is C6H5, is called phenyl group. So these two groups specially are having the special name. Now come toward this one. Once again, I'm going to write the name that is having two minor substituents. These all three are the minor substituents, not the major substituents or major functional group. These two are also known as, are regarded as the minor substituent. But in this case, there are two type of minor substituents. As I told you, the benzene ring will give name in coordination with OH group. So you will write the name of a compound of the benzene ring in attached with the OH. I mean, you will write phenol instead of this compound. Now you will write these Br as a branches. I mean, these halo group like this chlorobenzene, but here it is not bromobenzene. It will be bromophenol. So what is the position of these 4 Br? I'm going to give numbering this Br. This carbon will be carbon number 1. Carbon that is attached with the OH group or with the main functional group, it is carbon number 1. So I'm going to start numbering from clockwise, and then I will check anti-clockwise as well. So carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, and so on. So if I'm going to move like that, then one Br is at 2 position, the next Br is at 4 position, the next Br is at 6th position. 2, 4, 6, tri-bromo. Name will be written in a similar way. Chloro, bromo, iodo for halogens. 2, 4, 6, tri-bromophenol. Same is the case if I'm going to mark numbering other way around. 1, 2, 3, 4, 5, and 6. Same numbers will be repeated. However, if I'm going to write another example over here, if I'm having this one structure, one Br is over here and one Br is over here. Now, how to mark the numbers, how to give numbers to these carbon atoms. Now, once again, I'm going to start from the clockwise, and this is carbon number 1, 2, 3, 4, 5, and 6. If I'm moving in this way, there are the 2 branches. One is lying at 4, other one is lying at 6. I'm going to add these 2 numbers. 4 plus 6 is equal to 10. Now, other way around, if I'm going to mark the numbering, I mean, I am using another color pen, and 1, it's 2, it's 3, 4, 5, and 6. According to these green numbers, what are the number of Br group? Here is a 2 and 4, that is equal to 6. So smaller sum will be preferred. I mean, you will mark numbering in anti-clockwise. Now this is the wrong number or wrong numbers. So then we will write 2,4 dibromo, 2,4 dibromophenol. Now in this case, in the this example, in this the last example, this one, this is called major functional group. Any functional group that is having C double bond O, that is, you can say a tip or trick, it will be known as, or it is said to be, major functional group. This is the major functional group. So its position, this carbon will be taken as carbon number 1, and its name will be attached with the benzene ring. Now this time OH will not be part of the name of the benzene ring. I mean, it will not be a phenol. This molecule, the name of this molecule is having no word of phenol. So what will be the answer? What will be the number? Basically, again, I'm going to mark numbering, and the closest one, OH group, is closest to this major functional group through 2 and 3 at 3rd position. If I'm going to mark numbering over here like that, 1, 2, 3, 4, 5. So if I'm moving like that, so OH group is going to have 5 number. That's wrong. I mean, it's the highest or higher number is not preferred. Smallest or smaller number is preferred. So that is 3 number. So what will be its name? Its name will be 3. Now this time OH group is behaving as a branch. As a simple substituent group, you will write hydroxy. 3 hydroxy benz. You will write just benz, not ene, benz OIC acid. So the name is 3 hydroxy benzoic acid is the name of this compound. Okay, now I'll come toward the next one, that is the different major reaction of benzene ring. Overall, you will have to remember this scheme. Overall, benzene ring can show only 5 reactions. Only 5 reactions are associated with the benzene ring in your syllabus. Just 5 reactions. Number 1, you can say, let's suppose, that is called reduction. I mean, benzene ring can behave like an alkene in this way. If I'm going to add nickel plus hydrogen plus I'm going to heat it at 300 degrees Celsius and I'm going to add pressure as well. So under such conditions, the carbon-carbon double bond network is broken and it is going to change into simply cyclohexane. This is called reduction, addition of hydrogen. This is a unique reaction of the benzene ring. Benzene is not an alkene. The other all 4 reactions, I mean, let's suppose reaction number 2, reaction number 3, reaction number 4, and reaction number 5. Let's suppose this is reaction number 1. All other 4 reactions are not showing such gesture, such style of reaction. No, they are not in all these 4 reactions. Benzene is not going to behave as an alkene. It's showing a unique, a different behavior. So there is only one reaction that is very much similar to alkene, that is this one. Come towards the next one, nitration. I'm going to show one H over here. Although all 5 H are present over here, but I'm going to show just one. In case of nitration, you will have to use nitric acid, fuming nitric acid, I mean highly concentrated nitric acid, plus fuming H2SO4, sulfuric acid, very much concentrated H2SO4, and plus 60 degrees Celsius temperature. So the basic purpose of this temperature, not beyond the 60 degree, is to introduce one nitro group on the benzene ring. So these 2 reagents are going to meet together to generate a nitro group, nitronium ion, NO2 positive ion, and this benzene will react with it instead of this hydrogen. And this hydrogen is replaced by nitro group. So in this case, in this way, we can form nitrobenzene. Nitrobenzene. So these are the condition and these are the reagent basically. Once again, these 2 are the basic reagent. In this case, this H2SO4, sulfuric acid, is basically behaving as an acid in this reaction, and this nitric acid is behaving as a base. It is a unique reaction. I mean, unusual reaction is this one, but this is an acid-base reaction, and they are going to bond NO2 positive ion. That is the main electrophile nitronium ion, and it is going to react with a benzene ring. Now the next thing is Fredel-Crafts acylation. This group is generally said to be, I'm going to place R over here, acyl group. This is an acyl group. O double bond C, and here must be any carbon, any alkyl group. For example, this one, CH3, this is called acyl or acylium ion. So benzene ring can be introduced to this group, or this group can be attached on the benzene ring without removing its carbon-carbon double bond. Just as a replacement, by removing hydrogen, we can introduce this group like that. So we have made it ketone. This is an aromatic ketone. Carbon, 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 3 consecutive carbon, and the middle of the carbon is having carbon double bond oxygen. So this is called Fredel-Crafts acylation. What are the reagents basically? Let's suppose I'm going to introduce this group. So I will write this group first of all, and then I will show a halogen, halo group or halogen. For example, I'm going to show Br over here. So this is basically ethanoyl bromide plus FeBr FeBr3 plus heat or sometime heat under reflux. And in this way, FeBr3 is going to snatch this Br because this FeBr3 is electron deficient molecule and it is going to gain the lone pair of this Br group. So it snatches the Br atom from this molecule, leaving behind this positive charge on carbon atom. I mean, here is the carbocation. So this carbocation that is an electrophile. What is an electrophile? Electron lovers. Any species that is having full positive charge or any species that is having partial positive charge are known as or act as electrophile. So in this way, we can remove the H. So finally, after reaction of FeBr4 negative, I mean, after snatching this Br, this FeBr3 will be changed into FeBr4, and here there is a removal of H positive ion. Basically, they mutually react to make FeBr3 back, and HBr is formed. So it means that this FeBr3, or sometimes we are using AlCl3, they are acting as a catalyst. So in this case, we have synthesized an aromatic ketone. The fourth reaction is alkylation. You can introduce alkyl group. You can introduce methyl, butyl, propyl, isobutyl, isopropyl, ethyl, whatsoever. For example, I want to introduce this one group on benzene ring. I want to introduce this one group, that is CH3, CH, and CH3. So basically, let's suppose I am attaching once again, one is hydrogen over here, and I'm going to attach Cl over here. So this is 2-chloropropane. Is the basic reagent, is the basic reactant of this reaction. And plus, I'm going to use AlCl3 anhydrous without water. I'm going to heat it, and once again the function of AlCl3 is to pluck this Cl atom towards itself and to generate a secondary carbocation over here. So this carbon will get one positive charge and this benzene will react with the positive charge, because benzene exclusively react with the positive ion. With the partial positive ions or with the complete full-fledged positive ion, because this benzene is an electron-rich molecule. It is having extensive delocalization of pi electron, so it will happily react with the positive ion, and so in this way we can make an alkyl benzene. So this is called alkylation. The last one is halogenation. Generally speaking, if I'm going to add simple Br2 aqueous, that is dissolve in aqueous medium basically, and there's no reaction. Benzene doesn't react with simple halogens. With simple chlorine, with simple bromine, no reaction. As far as your syllabus is concerned, Cambridge A2 chemistry is concerned, you are just concerned with the two halogens, Cl2 and Br2, not with iodine, not with the fluorine. So you will be asked just the reaction of Br2 or Cl2 with the benzene. So there is no general simple reaction. I mean, this benzene ring is reluctant to react with normal Br2. Again, you will have to use either FeBr3 and heat under reflux, heat. Then there is the formation of Br positive ion, and then there is the introduction of Br group on benzene ring. So finally, we can make bromobenzene in this way. So these are basically 5 major reactions of benzene ring. Those are, repeated again and again in different topics. There is no any other reaction that is associated with the benzene ring in your A2 Cambridge chemistry. So you have to just learn these overall 5 reactions. Now the next one here, sometime side chain may also react. So in this case, you can see that this is the part of your AS chemistry. If I'm going to introduce Cl2, but I'm going to change the conditions. So if I'm not using FeCl3, AlCl3 or FeCl3 or FeBr3, and if I'm using UV light instead, then there will be no reaction of benzene. The basic purpose of this reaction to show you is that benzene is not going to react with the halogen if you are not using AlCl3, FeBr3. So what will happen? This is the alkyl group. Here is a UV light. This chlorine will change itself into radicals. So there will be the radical reaction. So benzene gives no radical reaction. Benzene gives no radical free radical substitution. This is the property of simple alkyl group to give the free radical substitution, and there may be the formation of many type of chloro compound. One of the possible answer is this one. One of the possible answer is this one. So conditions are important if you want to react benzene with a certain special reagent. Now come towards the phenol. Here's the phenol. I have divided this phenol into two portions. Some are the red reaction shown by the red color and some with the blue color. Basically, you can see that this phenol is having two groups. One is this OH group and other one is the phenyl group. So phenol is going to show basically two type of reaction with respect to its structure. These three reactions are because of OH group, and the other one reactions are basically due to the benzene ring. These are basically benzene ring, due to benzene ring. As I told you, whenever there's involvement of the benzene ring, there are only maximum 5 reactions in your syllabus, just 5 reactions. But if the OH group is supposed to react, then there are 3 reactions. So overall maximum reaction in your syllabus as far as the reaction of phenols are concerned is equal to 8. Now let's see over here. If I'm going to add sodium, that is a highly reactive metal, you know it, and it will react with the phenol to make a phenoxide ion or salt, plus hydrogen gas is released. If you are going to introduce this ethanoyl chloride in coordination with NaOH, NaOH is very important. If you're adding NaOH and then if you're adding this ethanoyl chloride, acyl chloride, then there is a formation of ester. You know that this phenol does not react with any carboxylic acid, no reaction. Phenol does not react with the carboxylic acid. Phenol does not react with the weak base like sodium carbonate, no reaction. Phenol, the OH group of the phenol react with sodium, very reactive metal. It reacts with sodium hydroxide over here, that is a strong alkali. With the reactive metal, especially metal, those are more active than the hydrogen atom in the reactivity series, and with the strong alkali like group 1 hydroxide. And it can also react with alkali, in the presence of alkali, with ethanoyl or acyl chloride to make ester. So there is only one way out to make ester using phenol, is this one. There is only one way out to make phenol. And same is the case, it can react with sodium hydroxide or potassium hydroxide to make a salt. This is simply a salt and water. Here's an acid-base reaction, and in this case there is only formation of salt and hydrogen gas is formed. So there are the basic major 3 reactions because of OH group. Now come towards if I'm going to add Br2 in phenol. Here there is no need of any catalyst. Benzene does not react with Br2. Aqueous bromine is not capable to react with the benzene. It's true, but it's not a benzene, it's a phenol. Benzene having OH group is basically now activated. It is more active molecule now. OH group has activated this benzene. Now there is no need of catalyst. Basically, when the pi electron of the benzene ring approaches this Br molecule, they polarizes themselves. One Br will get partial positive charge, other will get partial negative charge, and again there is basically a heterolytic fission. I mean, the bond is going to be broken unevenly and it will be shifted towards one Br or with this benzene ring. I mean, and the next one Br is going to be formed with full-fledged Br positive. I mean, in this Br2, once again, I'm going to repeat my theme. This Br will automatically break into two pieces. One piece will be Br negative plus other will be Br positive. So you know that benzene ring has attraction for positive ions only because it is an electron-rich molecule, it is an electron-rich center, so it will attract Br positive ion. And in this way, there is basically the formation of Br group over here. So we can say that Br over here, Br over here, and one Br over here. Because it is an active molecule, OH activate the benzene ring, and now benzene ring will react with 3 Br positive ion. This position is generally known as ortho position in a common nomenclature. This is again ortho position. This is called para position. And you know its position is equal to 2 as well. This is position number 4 in new nomenclature, and this is position number 6. So 2 and 6 are also known as ortho position. So 3 Br will be introduced on the benzene ring, and this is white solid, that is also said to be white precipitate. So in this way, phenol react, benzene ring of the phenol react with Br2. Same is the case if I'm going to introduce this one, there is no need to heat. Just simply speaking, when AlCl3 is mixed with this reactant, that is chloroethane, and it will snatch Cl, this carbon will get positive charge, and this OH group, I mean this benzene group can get CH2, Ci3 over here, but more chances are to be over here because of steric hindrance. These are the two main group, two bulky group you can say. They cannot sit side by side on the benzene ring. So major compound is, you can say, this one. So OH group is activating group, number 1. Number 2, OH group is going to direct the new incoming groups towards ortho and para position. So OH group is OP director as well. The next thing is, in this case, if I'm going to react it with this one, if I'm going to mix AlCl3 and this ethanoyl chloride, not, with NaOH. This was the different scenario when I mixed NaOH and this one, ethanoyl chloride. Now I'm going to mix AlCl3 and this ethanoyl chloride. And what will happen? There is the formation of, at para position, there is the introduction of acyl group. So there is acylation. There is acylation on para position. The last one, if I'm going to add dilute nitric acid, then you know the HNO3 is the major source of NO2 positive ion. So in case of dilute nitric acid, only one nitro group is introduced on one phenol. It may be over here or it may be over here. Only one nitro group is introduced. These both isomer will be formed. But if you are using concentrated, in case of concentrated HNO3, so there will be the formation of trinitrophenol. There will be 3 nitro group. In case of concentrated nitric acid, NO2, and NO2 will be there. So in this case, basically, there is multi-nitration on the phenol. These are the major reaction of phenol. Come toward the next one, that is the comparative reactivity. As I told you, phenol is a more reactive compound than benzene. And first of all, I want to show this page to you. Basically, if the benzene ring is having NH2 group, if it is having OH group, if it is having alkyl, especially CH3 group. So these three groups are called activator. They are going to activate the benzene ring because they are donating their lone pair of electron. In these two cases, they are donating their lone pair of electron to this convoy of pi electron system. I mean, they are going to relocalize their lone pair with the pi electron of the benzene ring. In this way, they are going to enrich benzene ring by or with electron. So when this lone pair is going to delocalize on this ring, electrons are basically going to have high density on these three positions. If any compound that is basically overall, it is delocalizing its lone pair to the benzene ring, indirectly it is going to increase the electron density on the benzene ring on these three positions. Yes, there is another effect. The effect is called inductive effect. This is an oxygen atom. This is a nitrogen atom. These atoms are electronegative atoms. Yes, they are snatching the electron towards itself. Yes, they are snatching the electron towards their self, but in these three cases, the basic effect is the effect of delocalization effect, that is also known as resonance effect. This is called a resonance effect. So basically, it's a complex mechanism. There are the two effects are mutually involved in this sort of scenario. Basically, there is a shifting of electron towards benzene ring, as well as they are snatching electron through the sigma bond of the benzene ring. Snatching electron from a sigma bond of benzene ring is called inductive effect. It's called inductive effect. If any group, if any atom, if it is snatching electron or pushing electron through sigma bond, this effect is called inductive effect. This is called inductive effect. For example, CH3 is basically electron showing the positive inductive effect. It is pushing electron away from it towards any other atom. So this is showing positive inductive effect. Positive inductive effect mean to push electron through sigma bond away from you, away from it. So this is called positive inductive effect. But what is the negative inductive effect? Like in case of HCl, in this molecule of HCl, Cl is snatching electron, these bonding electron toward itself. So sigma bond, Cl is snatching electron through sigma bond to itself. So it is showing negative inductive effect. So basically, inductive, i.e. inductive effect. Basically, there are two major phenomena are in operation. Generally speaking, you will have to learn this name. NH2 group is activating group, OH group is activating group, CH3 is activating group, but it is the less or least activating group. So under these conditions, if you are using phenylamine to react with any other molecule, if you are using phenol, so there is no need to add catalyst, there is no need to add heat. Especially, there is no need to heat the reaction mixture because they have activated these benzene ring. This is the least activating, here we use the normal condition. Same is the case on the other hand, NO2, nitro group. NO2 group, one of the possible structure of the nitro group is this one. N positive charge, O negative charge, and here is the benzene ring. So this is called nitro group. Benzene ring is attaching with an atom that is having positive charge on it. If any atom that is on the benzene ring and it is having positive charge, it is going to snatch electron from the benzene ring, away from the benzene ring. So it is going to decrease the electron density from the benzene ring. It is going to decrease electron density from these position from the benzene ring. So comparatively, comparatively electrons are enough on these two positions. These are called meta positions, commonly known as meta positions, or these positions are called 3 and 5 position. So NO2 group is deactivating group, C triple bond N is deactivating group, C double bond OH, aldehydic or ketonic group is a deactivating group. Any C double bond OH is deactivating group. In fact, carbon oxygen group, that is called carbonyl group, is deactivating group. So basically, whenever the benzene ring is attached with the C double bond O, it is going to deactivate the benzene ring. So whenever they are deactivating the benzene ring, again, the same position are going to be deactivated. They were activating these three positions. They are deactivating these three positions. So in this scenario, only two positions are left for incoming electrophile to attach with the benzene ring. So this is activating, deactivating, and directive influence of the sum group. Now, side chain reaction and formation of benzoic acid. This is called methyl benzene, as I told you. If I'm going to heat it in the presence of alkaline KMnO4 and then I'm going to acidify it, then there is a special oxidation that you have not been introduced in your AS chemistry. That is, alkyl group is going to oxidize. This is the side chain, side alkyl group oxidation. Only KMnO4 can perform this job. Initially alkaline but hot, then we are going to add acid into it. So if there is one methyl group, only one carbon atom is present, or if there is more than one carbon atoms are present on one bridge, on one corner of the benzene ring. If one carbon of the benzene ring, either it is directly bonded with the one carbon or it is bonded with more than one carbon. Simply speaking, one carbon will be left. All other bonds are broken, you can say. This is the simple theme or story that you will have to remember. So I am going to write it once again. What you will think and what you will do, that is, you will break these bonds. Number one, only one carbon should be left. Suppose three hydrogens are there. For example, I'm going to break these three hydrogen as well. Just one carbon is left. Then this carbon will be changed into COOH group, into acidic group. So this is the basic mechanism. If one terminal that is having carbon with other alkyl group or with hydrogen, with other normal alkyl group, if the alkyl chain is present on this carbon atom or there is no alkyl chain on the carbon atom, then this carbon, this only one carbon, it will change into acidic group. These both molecules, these are not the same molecule. These both molecules will make benzoic acid, only one same single product as an aromatic acid. So aromatic acid will be same from these both compound, although they are not same compound. But there is another scenario that is sometimes asked in past paper. This one, that if the side chain is common between two benzene ring, it cannot be changed into acid. If a side chain is common between two benzene ring, then it cannot be simply oxidized. Point to be noted. Here are two hydrogen atoms. Yes, if any carbon, if it is having two or more than two hydrogen atoms, it can be oxidized. But the basic pre-requirement is it must not be attached with two or more than two benzene ring. If this CH2 is present between these two benzene ring, so it can be oxidized, but this group will not change into acid. This carbon will not change into acid. It cannot be changed itself into acid. It will change into ketone. So removal of two hydrogen, yes, it is called oxidation, and there is introduction of oxygen. So this is a diphenyl ketone is formed. Basically a ketone, a new functional group is going to be formed. But this side chain will never go to make, carboxylic acid. So there are the different things. Number one, once again, I'm going to repeat my theme of this page. Basically, if only single carbon is attached with the benzene ring or any alkyl group, whatsoever its length, it may have 6 carbon, 8 carbon, 10 carbons of. So alkyl group can be changed. Normal alkyl group can be changed into carboxylic acid. This is not the alkyl group. This is not the normal alkyl group. Even if I'm going to write another compound, just for example, it is having carbon, another benzene ring, and other benzene ring, and here is one hydrogen. And if I'm going to introduce KMnO4, and I'm going to add acid plus heat for a long time interval, it cannot be oxidized. This carbon cannot make C double bond O because there is only one hydrogen. These bonds can never be broken. So C bond, carbon benzene bond, this is side chain carbon. Side chain carbon benzene bond will remain, or it will intact with the benzene ring. It will not broken by the oxidation method and so on. So this is the basic theme of side chain. Now benzoic acid can react, or other acids can also react in different way, especially benzoic acid. Benzoic acid, this reaction is basically from AS chemistry. You can introduce PCl3, you can add heat plus heat, PCl5 plus RTP, SOCl2, again at room temperature and pressure. So you can change this OH group by Cl, by one of these 3 reagents with the same, described condition. So you can change acid, any aromatic acid or aliphatic acid, normal acid, into basically acyl halide or acyl chloride. This is called benzoyl chloride. Benzoyl chloride. Now there are the 2 unique reactions for these 2 acids. Normally carboxylic acid cannot be further oxidized, but there are the 2 acids, those can be oxidized. Number 1, this is called methanoic acid. It is methanoic acid, methanoic acid, methanoic acid. It can be further oxidized into CO2 and H2O with the help of Fehling's reagent. Copper ion dissolved in sodium hydroxide. With the Tollin's reagent, that is silver amino complex in alkaline medium, or with KMnO4, or with K2Cr2O7. So using any of these 4 reagent, any one of the 4 reagent, even Fehling solution, that is a mild oxidizing agent. Tollin's reagent is a mild oxidizing agent. That is, these 2 reagents are basically used to oxidize aldehyde only, but they can also use to oxidize this one acid, because the one of the portion is similar to that of aldehyde. So methanoic acid can be further oxidized into carbon dioxide and water by using one of the possible these 4 reagents. The strongest one is KMnO4. Now come to the next one. This is called ethane dioic acid. Ethane dioic acid. Ethane dioic acid, and only in case of KMnO4. आप यहाँ पर कोई और reagent use नहीं कर सकते. You will have to use acidified KMnO4 only. If you want to oxidize this carboxylic acid, you will have to use KMnO4 only. Acidified hot KMnO4, and this molecule will change into CO2 from these 2 groups, and these 2 hydrogen will change into water. Once again, outcomes are pretty same. So they both are going to make carbon dioxide and water. So these are the typical reaction. Please remember them. Next one is acyl chloride. As I told you, how to make acyl chloride. you can make it from any acid. It may be aromatic acid, it may be an aliphatic acid. So by introducing, adding PCl3, PCl5, SOCl2, even sometime red phosphorus plus Cl2, or sometime concentrated H2SO4 plus NaCl, you can replace OH group with Cl group. This is the synthesis of acyl chloride. Now there are basically 5 major chemical reaction of this acyl, and specifically speaking, it is ethanoyl chloride. ENOYL, its name. I mean the name of basically the name of total carbon, 2 carbon, carbon single bond, ene, and the functional group is oil. Next we will write halogen chloride. So the name is ethanoyl chloride. If you're adding at room temperature, if you're adding water into it, this is called hydrolysis, and this bond is broken down immediately, rapidly, and there's formation of HCl gas, white fumes or misty fumes. Basically, this is a vigorous reaction. This is exothermic reaction, vigorous reaction, and so on. And there's the formation of a carboxylic acid. If you're going to add any alcohol into this compound, into ethanoyl chloride or acyl chloride, there is formation of an ester. Again, there is no need to heat. It's a very reactive reagent, so it will react with water, it will react with any alcohol, and there is formation of, again, misty fume or white fume, and there is a formation of ester. They also react with NaOH in the presence of NaOH with phenol, as I told you in the section of phenol, and there is an aromatic ester. So again, this is a new type of ester that can be made with the help of this one and with phenol. Now you can react it with ammonia, NH3, simple NH3. Again, NH3 will attack on this carbon atom and it will remove Cl, and here is a formation of NH2 CN bond, I mean imide is formed. So you can synthesize imide from this ethanoyl chloride. Similarly, if you're having primary amine or if you are having secondary amine, any type of amine can be reacted with this group. And it can make the similar respective imide. So you can make imide with the help of imines. This compound can react with simple ammonia. This compound can react with primary amine. This compound can react with secondary amine, and so on. I mean, these are the basic major reaction. Next thing is the other one, nitrogen compound, how they can be synthesized. I mean, simply amine and amides, you can say. So how to synthesize primary amine in this case? First of all, the one possible method is to use haloalkane. In haloalkane, I'm going to add NH3, ethanol, pressure, and heat as well. So the first of all, in stage 1, these both reactions are consecutive reactions. It is essential to report these both reactions whenever they are asking for the formation of primary amine. At stage number 1, there is the formation of this NH3 positive ion plus Cl negative ion. Then I am going to repeat this reactant over here. Another molecule of ammonia will react with this one. It is going to snatch one H from this molecule, and it is making itself NH positive ion. Here Cl negative ion. They both are making NH4Cl. Now in second step, there is formation of primary amine. This is basically primary amine, ethanamine. So this is two-step synthesis. As far as my opinion is concerned, as far as my experience is concerned, you should write 2 lines, 2 reactions for the synthesis of any primary or secondary amine. Now in this case, if I'm using, this is basically not ammonia, this is basically primary amine. Similarly, primary amine and the same haloalkane can react. This is a nucleophile, incoming nucleophile. It will attack on this carbon atom. Cl has to gone. So this is the formation of a secondary amine. So in this case, I'm going to make secondary amine, and every time there is the formation of NH4Cl. Yes, this step is also, this reaction is also consist of two steps. First, there is the formation of NH2 positive ion. Then in next step, NH3 is going to react once again. 2 mole of ammonia or 2 mole of alkyl amine may be used. Next thing is you can synthesize from this amide. Using amide, I'm going to add lithium aluminum hydride plus ether. I'm going to make this one amine and H2O. This is called reduction, and you have been taught in your AS chemistry. So by reducing amide with the help of haloalkane, the last one by reduction, by reducing nitrile. This is nitrile. So if I'm going to add lithium aluminum hydride plus ether or nickel plus hydrogen plus heat, you can use both option over here, and again the result is primary amine. So in all these two cases, you can make primary amine plus water is synthesized. So 1, overall 2 and 3. There are 3 basic way out to synthesize generally primary amine. You can also make secondary amine by starting from the halogen. So haloalkane, not halogens, haloalkane. Starting from haloalkane, you can synthesize primary amine. Using haloalkane, you can convert primary amine into secondary amine, and even you can convert secondary amine into tertiary amine. So with the help of haloalkane, you can synthesize primary, secondary, and tertiary. But if you're starting from amide, you can prepare only one amine, that is primary amine. If you're starting from nitrile, you can make only one amine, primary amine. The next thing is how to synthesize a special aromatic amine. Yes, it is a primary amine, but it is aromatic amine. So there are basically different conditions: heat and plus tin, concentrated HCl, and at the end we are supposed to add OH group into this whole mixture. So generally speaking, whenever you are supposed to make NH2 benzene, that is aniline, and its second name is phenylamine. So phenylamine and aniline. So you will start from the nitrobenzene. You cannot synthesize this molecule directly from the benzene. You cannot synthesize. Aminobenzene, it's also known as aminobenzene sometime, but aniline or phenylamine can be synthesized only directly from nitrobenzene. Yes, nitrobenzene can be synthesized from benzene. You can synthesize nitrobenzene from benzene, but NH2 benzene, this benzene cannot be synthesized directly from benzene. Next thing is, again, as I told you, it is an activating group. This one, it has activated 3 position, that is called ortho. Para positions are 2, 4, 6 position. So even at room temperature, without heating, with aqueous bromine, tribromo aniline is formed. This is also a white solid or white precipitate is formed. There are some other reactions. This phenylamine is reacted. That is a very, very important reaction as far as the color chemistry is concerned. If I'm going to add NaNO2, HCl, or already made HNO2 at 0 to 9 degrees Celsius, there is formation of diazonium ion. So there is formation of diazonium ion. So on first stage, if this compound, it is a very, very important compound as far as the textile industry is concerned. This compound, this phenylamine, can be changed into this diazonium ion or diazonium chloride. That is a salt basically. You can call it a salt as well. So this is the first step for the synthesis of dye. If I'm going to add any other aromatic compound like phenol into it, they are both meeting together in the presence of NaOH to make an organic dye that is having N double bond. how this die is formed, how to write the structure of this die, it's very simple. I mean, this here is this one diazoniamine. This one is called diazoniamine. I'm going to write it over here once again. This is a diazoniamine and triple bond. This middle N is having positive charge. It is supposed to react with phenol, like phenol. So how to make the final compound? So this one of the triple bond will shift on this benzene ring at the para position of OH group. You will attach, you will shift this bond between this nitrogen and this carbon where there is the para position or where there is the fourth carbon atom with respect to OH group. So I'm trying to write it once again. This is N and double bond. One bond has been shifted on this position of phenol, and you can see it's a para position with respect to OH group, or it's a fourth position. Now it has become an azo dye, it's a color, and the color of this compound is because of this N double bond. By changing different substituent on these group, on these benzene ring, you can change the intensity of the color, you can change the shades of the color, and so on. So basically, this is very much important reaction. I mean, nitrobenzene can be changed into phenylamine, and phenylamine can be changed into diazoniamine. Diazoniamine can react with further aromatic compound to make azo dye. This is one of the very, very important reaction. The next important reaction is the shortcut way to make phenol. There is no any other shortcut way to make phenol. There is one way to make phenol, that is from this one. If we are starting from the very beginning, benzene will change into nitrobenzene. Nitrobenzene will change into this aminobenzene or phenylamine. It will change into this diazoniamine, and it will finally change into phenol. There is no any shortcut. If you start from benzene ring, if you want to change it into phenol, so step 1, 2, 3, 4, at least you have to perform 4 steps. So to make phenol, and here you will add water, and just you will raise the temperature above 9 degrees Celsius by putting the water into it, and by raising the temperature there's a hydrolysis, and this N triple bond will go, it will leave the benzene ring, and there is a formation of OH bond or OH group. So in this way we can synthesize phenol. Now come towards the mechanism. Benzene ring exclusively give electrophilic substitution reaction. Benzene ring exclusively react with electrophile, and this reaction are said to be electrophilic substitution mechanism. What is the basic mechanism? In first step, electrophile is formed. How it's formed, as I told you in my previous, on the initial part of this lecture. For example, I'm reacting Cl2 with AlCl3. You know this AlCl3 is electron deficient molecule. It will snatch the Cl with its lone pair. So first of all, there is formation of AlCl4 negative ion plus Cl1Cl is changed into positive ion. It has become an electrophile. So the first step is to generate the electrophile. Now, this is the basic theme of mechanism in this line. Mechanism started now. One of the pi bond of the benzene ring, or if you are using circle, then you can simply start arrow from the benzene ring outside the benzene ring towards that positive ion or to partial positive ion. There may be any partial positive ion atom. So the pi electron of the benzene ring will attack on its neighboring electrophile. This is curly arrow number 1. So what will be formed? Here is the formation of H positive ion. There is one H positive ion, that is I'm going to show over here. As I told you, all carbons are having one H. There is H, not H positive ion, sorry. H atom is over here, same it's over here, and its bond this one, pi bond attacked on this electrophile, so it has been shifted outside the ring. With it has make a sigma bond with this electrophile. Initially it was pi bond, now it has make sigma bond. So this is the transformation of sigma to pi to sigma bond. The remaining, there will be one positive charge on this carbon atom, and remaining double bond will intact with this molecule. This is called rhenium ion intermediate. You can also write this molecule like that. जिसको उर्दू में चांद तारा जैसे हम बोलते हैं. So you can write this one. So you will start this line, this curve from this carbon till this carbon, not including this carbon, and you will write positive charge over here. And here is the hydrogen, here is the electrophile over here. In next step, this H bond, CH bond, is moving back inside the ring. Inside the ring, it is basically snatched by this AlCl4. AlCl4, I mean negative ion, will snatch this hydrogen, and this CH bond is broken and it is shifted back towards the benzene ring. Or initially it is a sigma bond, and when it is shifted back, now it has changed back into pi bond. So initially pi bond was changed into sigma bond. Now sigma bond has been changed into reverse pi bond. And in this way, this benzene has a new life. I mean, it has restored its life back. It has its aromatic character now. I mean, during the course of this reaction, there is little bit disruption of a discontinuation of aromatic character in the benzene ring, but it has restored its aromatic character again. But now it is having a new group on it as a replacement of, as a substitution of hydrogen. And here is the formation of this will attack with this one. If you are not using AlCl4, then you will simply write H positive ion. Again, I'm going to tell you, if you are not mentioning AlCl3 or AlCl4, then you will write H positive ion. If you are mentioning AlCl4, then you will write HCl plus AlCl3. I mean, this is the optional. This is the general mechanism. Every time you will mark two curly arrows, you will make rhenium ion intermediate. This is also said to be pi complex or sigma complex intermediate. And this is the final substituted product plus H positive ion is over here. This is general mechanism to be reported. Next thing is addition elimination, one of the famous and most oftenly asked question. This is called addition elimination mechanism. This mechanism is basically shown by this acyl chloride. So what is the basic step? Step number one, you will mark partial positive and partial negative charges on C double bond O. Yes, you can mark over here partial negative as well. I mean, it will not be wrong. Now, the next thing is, here are two lone pair on oxygen atom. You will mark the lone pair. So in this mechanism especially, you will mark partial positive, partial negative, and lone pair on the oxygen atom. First attack will be from this lone pair on this benzene ring. First curly arrow. This is a lone pair, this is a nucleophile. It will attack on this carbon atom, and you know carbon atom has already made 4 bonds. It cannot make 5 bonds. Impossible. So at the same time, this CO bond is broken, and the shifting of bond is shown by a second curly arrow. It will jump towards the oxygen atom. It will make O negative ion over here. So in first step, you will show partial positive, partial negative charges, and you will make attack of lone pair on this carbon atom. In this way, there is the first attachment of water molecule with this molecule. Overall molecule is neutral. Overall molecule, this whole molecule is still yet neutral. But in this one step, there is addition. You can see that there is addition. I mean, 2 molecules are added up. So that's why it is called addition. First step, I mean, its name is addition. Then what is the next step? This negative charge will come back on its original position, C double bond O, At the same time, CCl bond is going to be broken. There is another step as well I'm going to show, but you don't need to show it. You don't need to show it. That is sufficient for you to show the mechanism up till now. Up to just overall 4 curly steps are required as far as A2 Cambridge Chemistry syllabus is concerned. But in fact, what is happening in this case, after this, its shape will be like that. C double bond O, CH3, O, H, positive charge, H, and plus Cl negative ion that is having 3 lone pair as well. So in next step, this lone pair will basically snatch this hydrogen, and this bond, OH bond, is shifted back towards oxygen atom. So one positive was initially. When this bond will be shifted on oxygen, it is going to make a negative charge. Positive negative will be cancelled out. Simply this compound is going to be formed, and plus there is HCl. But you are not needed. You are not supposed to write this third step. Just mark or make these 2-step mechanism, and this is called elimination. Why it is called elimination? The first step is addition. In second step, we have eliminated a small molecule, H from one side, Cl from other side, HCl. So the second step is called elimination. So elimination, addition, elimination is the mechanism of this name of this mechanism, and you will have to revise it completely or fully. The next thing is how to write the answer for the comparative acidities and how to write the order of the comparative acid. First of all, number 1, any mineral acid like HCl, like H2SO4, like HNO3, these are highly stronger acid. Number 1, mineral acids are at the top. Then number 2, see which one acid is having this one group. On the second number, any acid that is having C double bond O group, it will be the stronger acid. In addition to that, check either the Cl is present or not. If any halo group is present on the next carbon atom, then it will be more stronger than that of normal carboxylic acid. It is normal carboxylic acid. It is halo carboxylic acid. It is called 2-chloroethanoic acid. It is simply ethanoic acid. So this Cl is basically electron snatching, electron withdrawing group hai. So basically you will check electron donating or withdrawing groups. So the basic competition is there any electron donation or donating group, or is there withdrawal of electron or any withdrawing group is present? On behalf of these phenomena, you can mark the order of the acids, stronger to weaker. Strongest acids are mineral acid. Then halo carboxylic acid, chloroethanoic acid, bromoethanoic acid, fluoroethanoic acid, and so on. Then simple ethanoic acid. After that, aromatic acid, like phenol. It's a phenol. Then here is the phenol. Then there will be water, and the least acidic is alcohol. It's the least acidic. Least acidic mean almost no acidic. So why is this so? Especially why these organic compounds are written in this order? The basic theme, the major theme is OH bond strength. This is having the weakest OH bond. This is having the strongest OH bond. So what is an acid? Acid is a species, a substance that is losing its positive ion in aqueous medium. If it is having strongest OH bond, it will not lose its positive ion. So it will be the weaker acid. If any acid that is having comparatively less stronger OH bond or weaker OH bond, it will be good acid. It will be stronger acid. So basically, this group is also said to be electron withdrawing group. C double bond O itself, C double bond O group itself is going to act as electron snatching, electron withdrawing group. In addition to that, we are having Cl group over here, If I'm having an other Cl group over here, it will be more stronger. If I'm having third Cl, it will be the strongest one. I mean, if you're going to increase the number of halogen on the side chain carbon, then indirectly you are going to increase the acidity of that carboxylic acid. So carboxylic acid basically is a stronger acid generally among all organic acids, and I mean, except water. Water is not the organic acid, generally speaking. It's a normal molecule. And these are the mineral acid, these are at the top. Then organic acid, those are having C double bond O. Then obviously phenol. And as this benzene ring is also snatching the lone pair of electron from oxygen, it's also going to weaken the OH bond. Water is going to behave as a normal molecule. Water, there is no weakening or strengthening of OH bond. No one is going to make this OH bond stronger or weaker. OH is normal neutral species just for the sake of comparison. And this CH2 group, as I told you, it is showing inductive effect, positive inductive effect. It is losing electron from its side. It is pushing electron from its side towards oxygen. So it is strengthening. It is going to make stronger the OH covalent bond. So these are the basic things that you will have to remember. You will, number one, write for 1 mark this whole order. Then you will discuss the weakening or the strength of the OH bond. Then you will basically show the delocalization or inductive effect. Inductive effect is only applicable in case of phenol, and in other cases, here is the delocalization of electron. Here is the delocalization of electron or electron withdrawing group. You can write, you can report in your answer over here. And the last one is stability of conjugate base. I mean, more stable the conjugate base, stronger the acid. Stronger the acid, and vice versa. So basically, if the acid is stronger, its conjugate base will be stable. It will not capture H positive ion again. If any acid that is a weaker acid, then it means its conjugate will be less stable, you can say. I mean, there is a stability basically. Stability of the base, conjugate base. If the conjugate base is stabilized or it is a stable one, then it means acid is stronger. If the conjugate base is less stable or it is not stable, especially in this case, you can write if it is losing H positive ion, then what is the remaining portion? The remaining portion is Ci3, CH2O negative ion. This is the conjugate base, and it is less stable or least stable. It is not stable. It will recapture the H positive ion and it will go back to make this ethanol again. So this is the basic theme. You will write the order first of all, as I told you under these instructions. Then you will discuss the OH bond, which one molecule is having stronger and which one is having weak OH bond. Then which one is showing delocalization of electron to make the bond weak, and which one is going to show or where there is inductive effect to make the bond strengthen. And the next one is stability of conjugate base, in which compound the conjugate base is stable or more stable and where it is less stable. Now the next thing is basicities. I mean, where there are basics or base compounds, those are having NH2 group. All these compounds are having nitrogen basically, like ammonia. You know, ammonia is a base, and this NH2 or NH3 group, any compound that is having nitrogen atom, and if it is having lone pair of electron, then it can act as a base. What is the base? Base is a compound that has capability to accept H positive ion, is called base. So which one is the stronger base? Which one is the weaker base? So in this case, basically, once again, here is electron donating or electron withdrawing group effect. In this case, I'm going to show you in a reverse way. The amides are almost neutral or least basic. They are not basic. This lone pair is no more available to capture the H positive ion from outside, from its neighbor. This lone pair is going to delocalize itself with this carbon oxygen pi bond, double bond. So there is the mutual delocalization of this lone pair. It is not available most of the time to capture H positive ion. It's the least basic. It is almost neutral. Now, then benzene is also almost also doing the same thing. That is, it is going to utilizing this lone pair of nitrogen towards its ring. It is also making it less basic. Not least, you can write it less basic. Ammonia is normal basic, but if ammonia is attached with the carbon, with CH2, with CH3, then simply speaking, they are going to strengthen the electron density on the nitrogen atom. So you will write your, the whole answer in this way. Electron density on the nitrogen atom is the greater, that compound will be the stronger base. The more basic character will be there. Like alkyl amines are the stronger one, there is positive inductive effect. Due to positive inductive effect, there is more electron density on the on the nitrogen atom. In phenylamine, there are weak bases because this lone pair is being used by this benzene due to or by resonance effect, by delocalization of electron. But in imide, this lone pair is almost completely utilized in this delocalization. It is no more available for outer H positive ions. So you will have to remember this one. Hopefully you will get the good result, or you will get the good point to report your answer. Comparative basicity, this is the one of the past paper question. I wrote it over here. The same thing is, here is the benzene ring. So it is going to delocalize over here. Benzylamine, this NH2 is having directly CH2 group. So here is positive inductive effect, basically positive inductive effect. Here is delocalization of electron. Ammonia is neutral like water. There is no, incoming electron density towards nitrogen in case of ammonia, or no one group is snatching the lone pair of nitrogen. So this is a normal base. Ammonia is a normal base. So basically basicity is linked with the lone pair of electron of the nitrogen atom. Alkyl group are donating electron to the nitrogen atom, showing positive inductive effect as I told you, and lone pair of N is going to delocalize towards the phenyl or benzene ring, so they are less basic in this case. The last topic of this day, this session, is this one, ease of hydrolysis. In hydrolysis, once again, the basic factor like acid is this bond, CCl bond. So once again, where the CCl bond is a stronger bond, it will be difficult to hydrolyze. Water will not break this CCl bond because it is the strongest one. The main factor is the bond strength. The second factor is it's a highly polar bond. It's a polar bond. It's a normally polar bond, and this is least polar bond. So, it's a polar bond, and this carbon atom is having partial positive, highly partial positive, you can say, and this Cl is having partial negative or highly partial negative. So this bond is easily broken by water molecule. Water molecule can break this bond because of the major two factor. Number one, it's a polar bond. Number two, its bond strength is less, right? In this case, it is going to show the normal behavior, CCl bond normally. However, this carbon is also, showing positive inductive effect in this case as well. But in this case, this lone pair of the chlorine is again going to delocalize on the benzene ring, and this phenomena is going to strengthen the CCl bond on the benzene ring. So acyl chloride easily hydrolyzed even with the cold water, because as I told you, because the weaker CCl bond, and then alkyl chloride are slightly difficult to be hydrolyzed. But aryl chloride or this chlorobenzene like that, I mean, they are very difficult, very, very difficult. Almost they are unable to hydrolyze themselves because of this delocalization and more stronger bond. That's all about this episode. Thank you very much. Please subscribe my channel, hit the bell icon, and share it with your friends. Thank you. Thank you very much. Have a nice day or have a nice night.